In response to this climate challenge, the 5-year Green Climate Fund funded project targeting supporting vulnerable communities in the Maldives to manage climate change-induced water shortages was launched by the government of Maldives in the year 2015. The accredited entity for the project is the United Nations Development Programme, and the implementer is the Ministry of Environment, Climate Change and Technology. This project has the objective to deliver safe and secure fresh water to 105,000 people in the Maldives in the face of climate change risks. Under this project, a consultancy service was carried under the title Assessing Groundwater Resources and Design of Aquifer Recharge Systems in Selected 17 Islands of Maldives, and this was 3 specific objectives as outlined. A. Undertaking baseline assessment to establish the current status and catchment characterization of each study island. B. Conducting feasibility study and developing concept design of managed aquifer recharge (MAR) systems for the islands with a specific emphasis on floodwater management. C. Detailed design for MAR systems. 2 videos were prepared under this project to explain and illustrate the activities carried out under this consultancy services and outcomes of the same. In this second video, explanations are given for how baseline conditions of the study islands were assessed, groundwater quality, quantity, and groundwater consumption by various sectors in the existing condition, and groundwater aquifer stress level were presented under this component. Methodology used for electrical resistivity survey to identify the depth to freshwater level and saline water levels from ground level were particularly explained. Methodology and finding of groundwater quality testing related to both physiochemical parameters and microbiological parameters. Details on social surveys and their findings. How topographical survey was carried out using drones and how GPS technology is being used for such a survey. Explanation is also added how images taken using drone cameras can be used to prepare land use maps. Finally, challenges faced under this study and limitation on outcomes of the study. Assessing. Development of the managed aquifer recharging system, which shortly called MAR, for an island requires consideration of 3 important items. A. Identifying the status of the aquifer and recharging rate in the existing condition. B. Identifying factors that influences groundwater quality and quantity. C. Developing MAR facilities with due attention to site conditions. MAR system is referred to a process by which a water is intentionally injected or infiltrated into ground or an aquifer. There are several advantages of an MAR system. For example, MAR system maximizes groundwater storage, it improves or at least maintains water quality, MAR system replenishes over-abstracted or depleted aquifers, and it maintains ecological systems dependent on aquifer springs or groundwater-based flows. Aquifer status and recharging rate. Identification process of aquifer status was done by comparing the available freshwater quantity in the aquifer and with safe groundwater extraction quantity. The quantitative volumetric estimates of the groundwater resource availability were derived based on the identified extents and thickness of the freshwater lens using electrical resistivity (ER) survey measurement. In the ER survey, resistance of the soil layer for passing the electricity is measured by driving a direct current signal into the ground, and based on the readings, freshwater level and saline level are identified. Resistivity survey can either be one-dimensional, two-dimensional, or three-dimensional. All these methods have their own merits and demerits. However, one-dimensional vertical electrical sounding (1DVES) method was chosen as the method for measuring resistivity of the soil, as this is relatively faster while giving the intended results with adequate accuracy. In 1DVES, the Schlumberger array method was used to estimate resistivity using measured voltage difference for a known current as shown in this diagram. The electrodes A and B are current electrodes, and they are connected to a current source, whereas M and N are potential electrodes which are used to measure the voltage difference. When the direct current or low-frequency alternating current is sent through electrodes A and B, the measured parameters like AB, current sent through, and voltage differences were used to estimate apparent resistivity of soil at different depths. They were then used to identify depth of freshwater level and depth of saline water level from the ground. ER readings were taken along many pre-identified profiles covering entire islands, and they were used to develop both freshwater level and saline water level contours. This map shows a contour map prepared using ER survey readings for Halif Filladu Island. This table shows freshwater quantity estimated for the study islands. The left side of the map shows the freshwater level. Color range from dark blue to green indicates the freshwater level significantly varies in the island. For example, the area shown by dark blue indicates that freshwater level is available in shorter depth from the ground level, whereas green color indicates that freshwater level is a bit deeper in the major part of the island and it is around 0.4 meters below the main sea level. Map on the right shows variation of saline water level over the island. Area shown by red color indicates that saline water is available in shallow depth in this area, whereas green color represents area that has saline water in deepest depth. Orange and yellow colors represent saline water at intermediate depths. By comparing maps on left with right, it can be interpreted that the freshwater lens is thicker in the island middle, but it is thin near the coast. This chart shows freshwater quantity estimated for the study islands. In the first study islands, the freshwater volume is the highest in Ta Kandudu at 1.5 million meter cubes and the lowest in Ta Gadifushi at only 68,000 meter cubes. Average freshwater lens thickness in these islands varies from 0.42 meters to 0.89 meters. In the second study islands, difference between freshwater volumes is not much compared to the first study islands, and it ranges from 254,000 cubic meters to 459,000 cubic meters. However, thickness of freshwater lens in the second set of islands are higher than the same in the first islands, and it is almost double. Reasons for such larger freshwater lens thickness for the second set of islands compared to the first set of islands is not very clear at this stage, and further hydrological and geological studies are required to understand the cause of variation. Recharging rate in the existing condition was estimated through water balance exercises, which involved collecting monthly rainfall from Hanimadu and Kaddu weather stations, estimating rainwater quantity harvested by island people, estimating evapotranspiration amount based on land use, etc. This flowchart shows water balance components of Ta Vandu, where around 740 people are living presently. Here are the key features notable from the flowcharts. Around 47% of water is lost to the atmosphere via evaporation and transpiration. Freshwater lost to sea is around 24%. Rainwater harvested by the island people in a year is 503 cubic meters, which is only 0.1% of annual rainfall received by the island. Around 30% of water goes into aquifers, and of it, 27% is being extracted by the island people for non-potable usage. Similar flow charts were prepared for each study islands. Groundwater is being extracted either manually from dug wells or pumped from deep well. These quantities often exceed the safe water extraction limits, which can be defined as the amount of fresh water that can be extracted without increasing the salinity concentration in the unconfined aquifer. These quantities were estimated from the water balance exercise, and they were compared with present extraction quantities and available freshwater volumes in each island. The outcomes of this comparison were used to identify the aquifer stress level. This chart shows that out of 10 islands studied, 4 islands, namely Halif Filladu, Halif Uligang, Halif Moladu, and Ta Kandudu, are in good condition, and their aquifers are not stressed in the existing condition. However, the aquifer status is currently not good in Halif Marandu, Ta Gadifushi, and Shavianifokadu Island, and managed aquifer recharging system should be implemented with higher priority in these islands to prevent deterioration of status of aquifer further and to bring them normalcy. Groundwater aquifer in Halif Muradu, Ta Omadu, and Ta Vandu Island are moderately stressed, and they also need managed aquifer systems implemented as soon as possible. Groundwater quality. Assessing the groundwater quality in the existing condition is a very important exercise since it helps understanding the extent of salinity level of groundwater and other water quality parameters. Two types of water quality parameters were measured. physiochemical parameters and microbiological parameters, temperature, pH, electrical conductivity, ammonia, nitrate, dissolved oxygen, turbidity, salinity, and phosphate were measured under physiochemical parameters, where total coliform and fecal coliforms were tested under microbiological parameters. Several maps were prepared to identify the distribution of each water quality parameters over the island using QGIS software and to understand status of water quality in the existing condition. This is a sample map showing the distribution of electrical conductivity and salinity in Kandudu Island. Here, electrical conductivity, EC, is a term used to describe a measurement unit of salinity, whereas the salinity of water is referred to a measure of the concentration of dissolved salts in the water. Hence, EC and salinity are related but not the same. Permeability test and infiltration rate. Field permeability testing in the unsaturated zone was carried out by measuring water absorbance at a constant waterhead in a 4-inch diameter hole dug with a fuel-driven mechanical auger to a depth of around 1.2 meters. The permeability test is a measure of the rate of the flow of water through the soil. A minimum of 5 representative locations were selected in each island, depending on the size of the island, land use, and hydrogeological and soil overburden characteristics. Groundwater usage. This was estimated through a social survey, and the categories considered for survey are water consumption by householders, water consumption by commercial outlets, cafes, restaurants, guest houses, water consumption for industrial activities, agricultural, lands, fish processing centers, others, and water consumption by institutions, schools, health centers, council, and other administrative buildings, etc. From this survey, it was found that groundwater usage is very high in the study islands and more than 90% in average for domestic usage. This table shows annual groundwater extraction of study islands and graphs shows groundwater consumption percentage by different sectors. Developing MAR facilities based on site conditions. There are many types of MAR structures, and of them, few are relevant to small coral islands like the islands in Maldives. Roof water recharging wells, infiltration drain, and recharging pits are some of the MARs applicable for the Maldive Islands. Roof water recharging through pit or well. Infiltration drain. Infiltration basin. Designs of the selected MARs were carried out with due to attention to following factors: rainfall pattern and intensity, soil characteristics and geological features, topography and land use, space availability for construction, social and environmental concerns. Each of the above listed factors were studies in detail to develop the conceptual design of managed aquifer recharge structures. Social survey, how it was done. A social or public survey at the island community level was carried out to understand the following: water sources, water usages and water consumption quantities, issues being faced in terms of water quality and quantity, flood inundation depths, frequencies and impact, expectation in finding solutions for groundwater issues, flood issues, and willingness to find the possible solution. Stakeholders included for social survey are householders, farmers, commercial and industrial sector owners, staff from Island Council, Magistrate Court, School, Health Centre, and FENAC Office. A summary of the procedure adopted for the social survey are: selection of number of households to be surveyed. Sample sizes were selected at 95% confidence interval. Also, location of households were selected so that the survey covers the entire island evenly. This map shows the households selected for the social survey in Halif Filladu Island. Given the COVID-19 situation, the surveys were carried out with the help of enumerators selected from the project islands. Enumerators were hired from the project island and trained to carry out the surveys. The training was conducted through online sessions using Google Meet and other platforms based on the convenience of the enumerators. An effort was made to provide equal opportunity, for both genders in selecting the enumerators. The research team at RIAN supported and supervised the enumerators on a daily basis. Preparation of questionnaire. It starts with collecting the number of members in a family to issues being faced. Most of the questions in the survey were relevant to quantification of daily usage of groundwater by each household, industries, and institutions. Individual interview. It was with selected individuals who possessed knowledge on island history and changes happened on groundwater quality and groundwater usage over time. This interview was very useful to understand population growth in the island over a few decades, groundwater usage in the past and present, when significant changes in groundwater salinity level was observed and what would be the probable cause, difficulties being faced due to higher salinity in the groundwater and possible solutions to overcome it. Topographic survey. Use of GPS coordinates, set up GPS system, land use characterization. Topographical survey was carried out with the purpose of determining ground level variation in the island, terrain shape, and boundaries. This survey was carried out for all islands using drone-based unmanned aerial vehicle that includes GPS and requires ground control points for mapping. These are some of the topographical maps developed using elevation data collected through drone surveys. From these maps, following features are observable. In Kandudu Island, the maximum ground level is 1.94 meters MSL and it is south of the island. There is low elevated area next to this higher land on the right side. Omandu Island is relatively flat and it has little higher elevated area at island middle and southwest of the island near the coastal belt. In Mandu, there is a stretch of high elevate sand dune along the west side of the island and ground level in major part of the island is around 1 meter MSL. Coordinate system in GPS, Global Positioning System. A coordinate system is a method identifying a location or point on Earth with unique two numbers like X and Y, northeast, or latitude, longitude, etc. There are several types of coordinate systems and each of them indicates distance of a point with reference to a fixed point. In GPS, coordinates of a location are usually expressed in alphanumerical characters, degrees, minute and second for latitude and longitude. GPS data is used in a variety of applications and embedded systems, including the following: mapping software such as Google Maps, ArcGIS, QGIS, etc. GPS data and devices are in motor vehicles, survey instruments like total station, marine vessels, fleet tracking and management systems, smartwatches, smart handheld devices, and laptop computers. GPS capabilities are often incorporated into digital accessories for outdoor activities such as cross-country running, skiing, and hiking. GPS and drone survey. Drone has an inbuilt GPS system and it records the position with respect to time when it is flying from one point to another. Prior to commencing drone survey, flying paths are set and transferred to drone so that the levels and images are taken with anticipated accuracy. Land use characterization using drone images. Images taken by drone can be used to generate high-resolution, detailed 3D models of surveyed areas and thus it enables producing high-accuracy cadastral maps quickly and easily even in a complex and/or difficult-to-access environments. Images taken from drone surveys of the project islands were processed and analyzed using other data like land boundaries, locations, and elevations to categorize the surveyed area into different land use like residential areas, commercial areas, forest, agriculture areas, bare lands, vegetation line, shoreline, etc., and also to prepare land use maps. Land use map prepared for Halif Marandu is shown below and similar maps were prepared for all study islands. Challenges, limitation. Few difficulties and limitations faced during the field measurement program are inaccessibility to survey location. Locations for electrical resistivity survey were predetermined using Google Earth maps and available land use plans. However, during a reconnaissance survey in the field, it was realized that some locations are completely inaccessible due to dense forest and marshy areas. It caused interpretation of freshwater level and saline water level using ER measurements of near locations. Permeability measurement. Permeability test is not carried out during the rainy period, as reading would be affected due to higher groundwater level. In some islands, it was fairly raining during the stay for the field work program. Therefore, a note on rainy day was taken down for the manual adjustment of the estimated permeability if necessary. As shown in the figure, during the rainy period, groundwater level rises and soil is partially filled with water. Therefore, the space available for natural infiltration becomes smaller. Hence, lower permeability rate can be expected during rainy period than non-rainy period. Bad weather. Sudden change in weather condition is a major cause for delaying field work, and it was very challenging to travel from one island to another and carrying out field work during heavy downpour. Restriction due to COVID. Fieldworks had to be carried out during COVID-19 pandemic, and many instructions were to be followed to prevent the spread of it. Moving around the island and working together in the field was not an easy task during the pandemic. The pandemic delayed the completion of the field work greatly, and even one of the islands were not given access.